Hello, everyone. My name is Harish, and I'm excited to walk you through my machine learning project. The goal of this project is to build a predictive model that estimates the electrical energy output of the combined cycle power plant based on the environmental conditions. The model is built using Python and follows the standard ML modeling process. Uh, so we move on to the next slide, which is the problem statement. To begin, let's understand the problem and the dataset. We are working with regression problem because we want to predict a continuous numerical output, specifically the net hourly electrical energy output represented as PE in megawatts. The dataset contains 9,568 rows, where each row represents a snapshot of environmental data and the corresponding energy output. The features include the ambient temperature measured in Celsius, V, which is the exhaust vacuum in centimeter Hg. AP is the ambient pressure in millibars, and RH is the relative humidity as a percentage. These features are collected via sensors at the power plant. The target we are trying to predict is PE, the net hourly energy output. Our challenge is to find the pattern in this data that can help us predict the PE based on the other four variables. Coming to the modeling approach, since we are predicting a continuous variable, this is clearly a supervised regression task. I chose root mean squared as my primary evaluation metric. The reason behind selecting RMSE is because it penalizes large errors and more so than the smaller errors, which is important when predicting energy output. Minor mistakes might be acceptable, but large deviations could lead to serious operational inefficiencies. I selected two models for comparison: linear regression, which is simple, interpretable, and serves as a great baseline, and a random forest regressor, which is a powerful ensemble model that can capture nonlinear interaction between variables. To validate the models before testing, I used a five-fold cross validation on the training data to ensure that our results are not biased by the single train test split and give us more robust sense of model performance. Model comparison. I have trained both models on the training data and evaluated them using RMSE, mean absolute error, MAE, and R squared on the validation folds, and then later on the test set. The linear regression model performed decently, but the random forest regressor consistently outperformed the linear progression. The random forest regressor produced lower RMSE, indicating that the predictions were closer to the actual value. It also has a higher R square score, which means it explains more of the variance in the data. These results make sense intuitively. A linear regression is limited to the modeling straight line relationships, while random forest can capture more complex interactions between features like how temperature and humidity might jointly affect output. Here is the plotting of the actual versus predicted output. Uh, on the scatter plotter, each point represents a prediction. The x-axis shows the actual PE values, and the y-axis shows the predicted PE value. The dashed line is the ideal scenario, which means the perfect prediction. As you can see, the predictions from the random forest, which are represented as circles, are clustered much closer to the line than the ones from the linear regression, which are marked with X's, cross. This visually confirms the numerical result. Random forest is doing a significantly better job of capturing the underlying pattern in the data. Beyond just performance, it's important to understand why the model is making the prediction it is doing in terms of interpretability. This brings us to the important feature importance here. Here, ambient temperature (AT) is by far the most important feature. This makes sense because temperature directly influences the turbine's efficiency. The exhaust volume comes next, likely because it reflects how effectively gases are being expelled. Relative humidity and ambient pressure play smaller roles, but still they contribute to the overall model and the final outcome. This kind of interpretability is very crucial in real world settings where operators might need to act on the model's recommendations. And to conclude, I think we clearly defined our regression problem and selected RMSE as an evaluation metric. We compared two models, linear regression model and random forest, Using cross validation and multiple metrics, random forest has emerged as a better performing model, both in terms of accuracy and flexibility. We also analyzed which features mattered the most in the prediction. The final model is robust, interpretable, and could be valuable in helping power plant operators optimize output, reduce cost, and plan for maintenance more effectively. Thank you so much for your time. And I should say, for a student, for somebody who has come from a non-math background, this tutorial has been pretty handy, and I appreciate you people taking time to peer review it. And I look forward to very constructive feedback from you people. Thank you, and thank you in advance.